All right, ladies and gentlemen, in this lesson we're going to consider exponential functions. And I think this topic in particular is really interesting because it often results in situations that are just like really hard to wrap your head around. This is the math of how the pandemic spread in the first couple of months. This is the math of why you should never borrow from like these types of places if you need to borrow money. And yeah, it's just the math of things kind of growing out of control, essentially. And people have been considering this type of problem for a very long time. So to introduce this idea, we're going to start with a story that is actually very, very old. It comes from India a very long time ago. And essentially you got two guys playing chess, and the winner, they make a bet, and the winner says, you pay me in rice. And the way you pay me in rice is you put 1 grain on the first corner of the chessboard, you put 2 grains on the second space, 4 grains on the third space, 8 grains on the fourth space, and so on, right? And then as the king goes to pay, he realizes that like he can't possibly pay that amount that he owes. So let's investigate this a little bit. So what I'm going to do is I'm going to fill in some numbers here. So we said 1 grain, 2 grains, 4 grains, 8 grains, 16 grains. So I'm already over 100 grains of rice by the time I get to this corner. And what I would love for you to do here is just make a prediction, like how many grains of rice are we supposed to fit on this last corner of the board. I'm going to continue filling in numbers until they don't fit anymore. And then about here, I'm just going to go ... because I'm going to have an extra digit and I'm going to have to really squeeze it in. So what we notice, right, is even the numbers get unwieldy. So I'm already at 65,000 and some change on my third row, and I still have 5 rows to go. By the way, feel free to stop writing these numbers down. You don't need to copy all of these down. Although powers of 2, if you are interested in studying computer science or anything to do with computers, you're going to start to see these numbers a lot. Now, I found an interesting YouTube video, maybe I'll link it for you guys, where a dude actually tries this. And what you can see is it gets really silly really quickly. And then he starts to use sort of bigger scales to start to represent the problem. So you can watch this if you're interested. I'll include a link to it in a pop-up here. So I want to consider maybe a more boring problem of like, these numbers get so big that I can barely even write them down, right? So I run out of space on my chessboard, right? And by maybe writing them a different way, we can find a representation that allows us to consider how much rice would go in this last spot here. So I'm going to use exponents here. So we know, like, I'm writing here just 1, and then 2, and then 2 times 2, and then 2 times 2 times 2, right? Well, really, that's 2 to the first, 2 squared, 2 to the third, 2 to the fourth then, right? 2 to the fifth. So what we see is by using exponents, I can analyze this situation a lot more easily. And 1, if we started with 1 here, well, 1 is just 2 to the 0 power, right? So the pattern holds. And notice I end on a 7. So here would be 2 to the 8th. And here I have probably 2 to the 15th, right? So if I continue the pattern, well, there's 64 squares on the board, but I started at a 0. So here we would have 2 to the 63rd power. And that's a number so big my calculator won't even spit it out for me. And what I did is I just Googled it, what 2 to the 63rd power is, and that's this number, right? And we can put in some commas so it's a little bit more readable, but I don't even know how to say this number. So here we're in the millions, billions, trillions, and I don't know what comes after trillions. Okay, so it's obviously more rice than would ever fit in the chessboard in my classroom. It's a lot of rice, more rice than anybody would ever want. Okay, so what we noticed on the previous page is that if we use an exponent, we can represent this situation a lot more easily than just writing down a big list of numbers, right? So if I want a function g of x, so that g is the number of grains of rice and x is the number of the square we're on, well, my function would be probably 2 to the x power, right? Would be more generally for an exponential function, we say we have something like f of x equals a b to the x power. where A is the starting value, so that's what we get, sort of like the y-intercept when we plug in 0, right? B is called the common ratio, or you can think of it as the growth rate. Okay, so notice our g of x had no A value, and that's really because we started with 1 grain of rice, right? So it would be 1 times 2 to the x power if we want to have an A and a B. All right, now we're going to consider my check cashing place. I chose this particular one. This is the one at North and Kimball because I used to live over there. So we're going to compare borrowing on a credit card, which is still expensive, to borrowing from one of these stores using an exponential function. And these are going to be sort of your models that you'll use to do your delta math and all that. So we'll write a function here. Our original cost was $350, so maybe we bought an Xbox or something. We'll write a function f of x equals 350 times something to the x power. And this would be my b value, right? The b value is a little bit harder to figure out. So we have a 23% interest rate. To do percent growth, it's a little bit trickier than just multiplying by 2 every time. What we do is we do 1 plus the rate. So here we would do 1 plus 0.23. Percent decrease would be the opposite, obviously. So obviously the 1 represents 100%. We're adding 23%. And then we would say 12 for 12 months for a year. And the result is not pretty, you guys. It's $4,196.91 after 12 months. Make sure when you type this in, this is an exponent, right? So you're not multiplying, and that's how we get this result. Now, if you thought that was bad, this is going to be way worse, right? So here, and this is about true in real life, if you borrow that same amount of money for $350, you owe $450 at the end of the month at this place. So this is a little bit more complicated because they didn't give us the rate. So we're going to use percent change formula here. It's not really a formula, it's just like how you do it. You do new minus the old divided by the old, and that gives you like percent increase or decrease. So here it would be 450 minus 350 over 350, which gives you, we'll do 0.2857, 28.57% is what it would be. So this is going to be even worse, I think, right? So here we would do 350 times 1.2857. And it's important to keep a couple extra digits here because any rounding error here kind of compounds on itself, so it'll make your answer very far off if you don't use those. And then again to the 12th power. And this time what I get for, we should say f of 12, is I get $7,141.70. So like surprisingly more than this, I would say, right? So yeah, check cashing store, bad deal. And notice like we're thinking of like no late fees and any of that. So actually in real life, these numbers would actually be worse. Especially like the check cashing store has tons of hidden fees and stuff like that, which is why some people think it's predatory that like these things show up most often in lower income neighborhoods. Okay, so here are two models that we can use. So notice here we found a percent change and then used it to write a function.